After installing the Isotope Pattern add-on, a new icon will appear on the right side of your spreadsheets. Clicking on this icon will bring up a new window on the right side. This new window is for calculating and plotting the first and second set of isotopomers. In this video, first I will show how to use this add-on, and then later I'll discuss some background information. This add-on is limited to the 10 elements shown here. To generate high-resolution isotope patterns, first the isotope sheet must be created by clicking on the Create the Isotope Sheet button. This will usually take 10 to 15 seconds. After this sheet is created, an elemental formula can be entered into the text box, and a resolution setting can be selected. Let us analyze the formula for atenolol C14H22N2O3. Clicking on the Generate an Isotope Pattern will start the analysis. The table on the left side of the sheet is a listing of various isotopomers, the occurrences per 10 million molecules, and the exact mass of each isotopomer. This table is subdivided into 3 sections. The top section is the monoisotopic molecule, which has a formula and the exact mass that are based on the most abundant isotope of each element. The middle section is the group of 5 isotopomers having masses about 1 Dalton higher than the mass of the monoisotopic molecule. The third section is the group of 19 isotopomers having masses that are about 2 Daltons higher than the monoisotopic molecule. Over on the right side are plots of the first and second sets of isotopomers. These are in the Google Sheets, and they're normal charts. So by clicking here, we can edit the chart. So for example, the first set of isotopomers, there are a couple of very small isotopomers. I can customize the vertical axis, and I'll make it 10 times larger and go to 2500. Can also we could also do other things like change the line chart into, let's say, a smooth line chart, and makes a little bit cleaner looking graphs. So now we can see clearly the O17 in green and the deuterium in orange. Let us look in the lower graph at the oxygen 18 isotopomers that are colored greenish blue. There are 3 oxygen atoms. A single oxygen 18 atom can be found in 3 different positions. The structures are not identical, but all will have the same exact mass. The raw data signals from your mass spectrometer will not deconvolute the individual isotopomers by color. To compare your results to instrument data, the graphs can be redrawn to show the overall outline of the sum of the individual isotopomers. So here we can edit. We can pick the stack column chart. And now we're just seeing the outline. It's a rather smooth outline. If you want to keep and compare two sets of results, rename your isotopes sheet and then create a new isotope sheet using the Create button again. If the same analysis is repeated, the masses will always be the same. Each isotope has an exact mass. The mass of a hydrogen atom or the mass of a deuterium atom is exactly the same everywhere in the universe. We can compare some experimentally determined masses of the monoisotopic isomer of etenolol, called accurate masses, to its monoisotopic mass. The small differences in mass are caused by experimental error. The exact mass of the monoisotopic isomer is often called the theoretical mass. Unlike theoretical masses, there are no theoretical isotope patterns, because isotope patterns are based on probabilities. Let us randomly generate one etenolol molecule. Imagine if there was a swimming pool with 100,000 ping pong balls representing the element carbon. This pool might have 98,930 black carbon-12 ping pong balls and 1,070 gray carbon-13 ping pong balls. Carbon-14 is about one carbon atom per trillion, so we can ignore carbon-14. Because we are generating an etenolol molecule, we will randomly draw 14 carbon balls from the pool to start making a molecule. We cannot add other elements to the carbon pool. For example, oxygen would be placed in a separate pool. The oxygen pool has 3 isotopes. Because etenolol has 3 oxygens, we would draw 3 balls from the oxygen pool. The same process would then be repeated to add 22 hydrogen balls and 2 nitrogen balls. These ping pong balls are replaced after each draw. The more molecules that we generate, the closer we would expect the ratio of isotopes in the sample will match the ratio in the pool. This add-on uses a random number generator to create a molecule and then repeats that process to make 10 million molecules. This sample size is much larger than what most mass spectrometers can collect in a single spectrum. Even with a sample size of 10 million molecules, the frequencies will vary slightly even if the same parameters are used to repeat the analysis. This graph illustrates that smaller samples of molecules will have much more variation than a larger sample. Here, the A+1 in blue is the sum of the first set of isotopomers, and A+2 in red is the sum of the second set of isotopomers for the formula of malathion. Although not addressed with this add-on, the ratio of individual isotopes of the same element varies with the sample. For every million atoms of the element hydrogen in a sample on Earth, we would expect about 26 to 184 occurrences of deuterium atoms. The ratio of deuterium to hydrogen is not fixed. The deuterium-hydrogen ratio of the atmosphere on Mars is about 5 times greater than the same ratio on Earth. Because a fixed ratio is needed for this add-on, our add-on uses the most representative values from reference 1. There are 2 reasons that there is no theoretical isotope pattern. First, the ratio of different isotopes for most elements is not fixed. Second, the sample size may not reflect the whole population.